about similarity, and it will involve a lot of different things. But when you're looking at similar figures, you're for sure going to have to do ratios, proportions, and then this added thing of geometric mean is just some added information. But first things first, do you guys know what a ratio is? What's a ratio? It's really just a fraction, isn't it? It's comparing two things using division. Now, here's the thing you've got to be... Hey guys, could you stop talking? Here's the thing you got to be careful with is that the order does matter. So if they're asking you to write the ratio of A to B, you write A on top, B on the bottom. Is everybody with me on that? Let's see. Oh yeah, another issue that can come up, especially in word problems, is that ratios are usually expressed in simplest form. So like they have here, two ratios that have the same simplified form are called equivalent ratios. For example, 7 to 14 is equivalent to 1/2, isn't it? But what you're going to find out is if they tell you in specific shapes that sides are in a certain ratio, you got to realize, well, that's not the actual lengths of them. They actually may be something bigger, right? So we got to be kind of careful with that. We'll see that in a couple of examples. Well, in example 1, it says to simplify the following ratios. So 26 yards to 12 yards. So we write it as 26 over 12. And from there, does it reduce?
Yes, sir.
It sure does, doesn't it? What is 26 divided by 12? Yeah, it doesn't divide nicely, so we're gonna have to reduce it, right? Yeah. Yes. What do you say?
I'd say do it by 2.
13 over 6. So we started with these actual values, but our ratio is something smaller. And notice to go back, we would times by 2 to each one to go back to the original values. Also keep in mind that ratios can be written like this with a colon, 13 to 6. It's kind of surprising. It's kind of surprising that you could do that. Yeah. Can't you really? Yeah.
Like if they gave you just the ratio and it wasn't like 13 yards to 6 yards.
Exactly.
Yeah.
Exactly. We're going to see that real quick. Yeah. So on example 2, now this example is kind of interesting because it's 36 inches to 9 feet. Well, you often see ratios that have different units. That's not uncommon. For example, miles per gallon. Isn't that a ratio that you see pretty often? You know, if you're looking at efficiency of a vehicle, or price per gallon if you're buying fuel. So it's common to have ratios that are different units, but this one wants you to get an authentic ratio comparing the same values. So what could we do here to correct this? Yeah.
I think we can make it 3 feet or 9 feet.
You could make it, so we could go 3 feet. Do you guys agree that that's equivalent to 36 inches?
Yeah.
Yeah, you could do 3 feet to 9 feet. And if you did that, you would get 3 to 9, which reduces to what? 1/3. Now, what's kind of interesting is that the only way you could have done that? You could have done 9 feet. You don't have to write this down, but let's just explore that real quick. 9 times 12, what is that? 108. So 36 to 108. By the way, do you guys know that your calculators can reduce fractions?
Yeah.
Have you guys ever done that? So I'll do 36 fraction 108. And looky there. Oh, it's hard to see, isn't it? But yeah, 1/3. So what's cool about it is, did it matter what units we switched it to? We still get 1/3 either way. Okay. Now let's look at example 3 and see if we can make some sense of this. It says the area of a rectangular garden is 108 square feet, and the ratio of the length to the width is 4:3. Find the length and the width of fence needed to enclose the garden. Let's draw a little picture. We've got a rectangular garden. We know that the area is 108 feet squared. The ratios or the side lengths are in a ratio of 4:3. So length to width. By the way, with rectangles, what's the length and what's the width? It doesn't really matter. But we're going to go 4:3. But here's the thing. Do we know that the side length is actually 4 or actually 3? No. And my guess is it's not that, because if we multiply those together, what do we get? 12. Is that even close? So what that tells us is these are actually going to be, the actual values are actually something bigger, right? It's something bigger. But what's good to know is isn't it up here, if we multiply both of them by 2, we got back to the original? So what we need to know is what value we need to multiply by is going to multiply both of them. So instead of thinking of it as 4 and 3, think of it as 4x times 3x. So 4x times 3x, that is going to equal the 108. Are you guys with me on that?
Yeah.
Okay. From there, it's an algebra problem, but is it one that you guys can handle? What is 4x times 3x? 12x squared. And have you guys learned what to do to get x by itself? Divide the 12 over, and then what? Square root it. What is 108 divided by 12? 9. Nice. And square root it. And we get x's value to be 3. Now, we came up with x on our own, didn't we? That's not what we're trying to find. What are we actually trying to find? The length and width of the fence, right? So what's going to be one of the measures? One of them is going to be 12. 12 what? Feet, yeah. And one of them is going to be what? 9. There we go. So it's a little bit tricky. Whenever they give you a ratio, keep in mind that it's probably some factor bigger. Some factor bigger. It could be smaller. Well, I mean, no, it shouldn't. It should always be bigger. But, so you just basically slap an X with each one, don't you? Just slap it on there. Yeah. Question? Yeah.
You said like with the rectangle it really doesn't matter, but since the ratio is like 4:3, would you need to keep it in that order, 12 to 9, and do you have to put it back in the ratio or no?
No, because they're just asking for those things individually.
Okay.
It doesn't matter. Yeah, it doesn't matter. But I like that you were concerned about the sequence of it. Will you guys take a look at number 4 and see if you can figure that one out? So notice it's an extended ratio. An extended ratio just means we're not comparing 2 things. In this case, we're comparing how many things?
3.
3 things.
Wait, how do you know what is what?
Yeah, you can just choose. Well, actually, hold on. The measures of the angles of triangle RST are in the extended ratio 2, 3, 4. So I actually don't think we can choose, Adalea. I think it's telling us. Yeah. So the 2 corresponds with what? R. The 3 corresponds with S. And the 4 corresponds with T. Are those the angle measures? No. What do we need to slap on each one of those? I don't know why I feel like saying that today. So yeah, you put an X with each one, because aren't they all going to be bigger by the same amount? Well, what do they all add up to?
180.
There we go. So we're going to have 4X plus 3X plus 2X is equal to 180. Those are all like terms. So I'm feeling a 9X is equal to 180. And that would mean X is what? 20. Were they asking for X? No, they were asking us to find the measures of the angles. So we got to take that X and plug it back in, don't we? What's the measure of angle T? 80 degrees. Measure of angle R?
40 degrees.
40 degrees. And the measure of angle S? 60 degrees. By the way, could you kind of check your answer? Do these add up to 180? They do. What do you guys think so far? Yeah, it's not so bad, I don't think. Oh, easy peasy. That sounds great. That sounds great. Okay. So, that was dealing with ratios. Well, along with ratios comes proportions. So I think in Algebra 1 you guys learned about proportions. I know if you had it with me, you did. A proportion is just a fraction equal to a fraction. You guys cool with
Say
that?
one more time.
A fraction equal to a fraction.
Oh yeah, I know.
You do? Okay.
Yep.
Well, yep, when two ratios are set equal to each other, this is called a proportion. Now, what's interesting about this is you'll hear people say it kind of in a weird way. They won't necessarily say the fraction A over B is equal to C over D. You can say it as A is to B as what? C is to D. When they talk about it that way, they're talking about proportions. Now, put a little star underneath here, and I want you to write that proportions are useful in solving many application problems. Oh, okay, maybe riddles. Application problems. And just a heads up, if you have a situation, oh, let me do it. If you have a situation where, like on the ACT, you're working a problem and you're like, ugh, I can't write an equation that works. Think about proportions, okay? Oftentimes, I know when I've been working through ACT questions and stuff, if I'm kind of stuck and like, I can't quite see an equation here, if I think about a fraction equal to a fraction, it works out, okay? Also, what you're gonna realize is that to solve them, you can multiply by both denominators. And that's the way I teach it, is multiplying by both denominators. And we'll talk about it on our first example. But after we do a couple of examples, students get wise to what I'm talking about. And they realize that multiplying by both denominators is actually, you know what, I won't tell you. We'll find out. We'll find out together. So take a look. Does everybody agree that example 5 is a proportion? Fraction equal to a fraction. Well, we're going to solve it for x. And one way to solve it is pretty easily on this one is, can't you just multiply by 27 and won't that get x by itself? Yep. So yeah, on this one you can multiply by 27 on both sides. And you're ready to grab a calculator and figure this out, aren't you?
Go back and figure it out in my head. 100.
Okay, I don't know why, but my brain was like doing something.
Well, no, you can also do this some other ways. Yeah, we'll talk about it. I bet Adelaide, you're thinking of something that I'm thinking of. Maybe.
Oh, 126.
Yeah, I was not have thought of that.
So, yeah, I just did 27 times 8 and then divided by what?
24.
Yeah, 24. What do you guys get? 9. Now, take a look at the next example, though. On our next example, we're not so lucky. For one, do you see how we've got 2 x's? For another, they are trapped inside the denominators. So what I like to do is, if it's in the denominator, I multiply by it to get it out of there. If I multiply by 4x, isn't it going to cross out here?
Yeah.
But do you see how if I multiply by 4x on the other side, it'll be up top now? Yeah, so that's the way I'm going to approach this. I'm also going to multiply by the x plus 3 because that will get rid of it on this side, but see how it'll move it to the top on the other side? So it looks kind of complicated, but do you guys see how the x plus 3 is gone? What are we left with on this side? 8x, 4x times 2. On the other side, the 4x's go away, and we're going to have to do what with the 5 and the x plus 3? Yeah, which means we're going to have to distribute. And we're going to get 5x plus 15. Is that a little more palatable at that point? Yeah, you can get x by itself. Subtract the x, the 5x over, you'll get 3x is equal to 15, or x equals 5. So, oftentimes, on a problem like example 5, instead of just multiplying by 27, guess what I also multiply by?
24.
Yeah, I'll multiply by 24. What it does is it just gets rid of the fractions right away. So it turns out that multiplying by both denominators, do you guys see how a set of 4x's went away?
Yeah.
A set of x plus 3's went away. What am I actually doing there?
You're just
Think-
taking the denominator out.
Well, yeah, but what are we actually multiplying? Aren't we actually multiplying 2 times 4x
Yeah.
and 5 times x plus 3?
You're cross multiplying.
We're cross multiplying. Yep. It turns out that to solve them, you can multiply by both denominators, but it's also, it ends up just being cross multiplication. Which I often don't like to do cross multiplication. I don't like to say it, but I do like to use it. It's quicker. Adelaide, were you kind of thinking about multiplying by both denominators? Or no?
And then I thought of it another way, but that wouldn't work.
Okay. Well, Example 7 says, as part of a science project, you need to estimate the number of blue spruce trees in a 50-acre forest. You count 36 trees in 3 acres, and notice that the trees seem to be evenly distributed. Estimate the total number of blue spruce trees in the forest. Now, we're using proportions, right? So think about this proportionally. Think about how you can write a fraction equal to a fraction. Did they give us a ratio?
36 over 3 equals
Yeah, 36 trees,
About 600 trees.
3 acres. I'm going to write a ratio from that. 36 trees over 3 acres. So 36 trees for every 3 acres. How many acres do we have?
50.
50 acres. So that ratio, if they're evenly distributed throughout the forest, this ratio should equal another ratio out of how many acres? 50 acres. 50 acres.
600.
And we're trying to find out how many trees, right? So what do you want to write?
X.
X. Are you guys okay with how we set that up? Yeah.
I did it a different way.
Okay. There's more than one way to do it, for sure. Let's see if we get the right answer though, okay? The way I set it up, we got 36 over 3 is equal to x over 50. You can multiply by both denominators. You could cross multiply, or in this case, you could just multiply by what? To get x by itself. Yeah, I'm just going to multiply by 50. Both sides. And then I'll do 36 times 50 divided by 3. Brady, what did you get?
600.
600. That's what I got as well.
I think you did the same thing.
Did you do it to 112 and then multiply it by 50?
Yeah.
So, one thing you will realize is that, in a way, these are kind of like hard to mess up. I could have done 3 over 36, and then I would have just had to flip this around, right? What's also interesting is I could have set it up like this. I could have said 3 acres over 50 acres, and then set it up with, since I did the 3 acres that was connected to the 36, first, I'd have to do 36 over x. That's another way you can set it up. You can set them up a lot of different ways. But Brady, how did you do it? What were you saying?
I simplified the 36 trees in the 3 acres first. There are 12 trees per 1 acre.
12 trees per acre.
And then I just multiplied that.
Perfect. Yeah, that's awesome. That sounds great.
Also, just multiply the 50 by 36 and multiply it by 3.
Do I know? I'm sorry.
You can just multiply 50 by 36 and then divide by 3.
And then,
That's
yep.
kinda what we did.
Yep, and mathematically, that's exactly what we got there. But yeah, you can think it through and multiply it out. Well, the last thing that I want to talk about today is something called a geometric mean. You guys have learned about other means in the past. You've learned about arithmetic means or arithmetic means. How do you find the mean of a group of numbers? It's the average. Yeah, you add them up and divide. Hayden, would you mind to turn around?
Yeah, I could. Sorry, I was looking at
That'd be great.
notes.
So I thought we talked about how you're not supposed to bring slushies in to this
Oh,
class.
shoot.
Do you remember that? Okay, tomorrow.
I forgot. Actually
No,
throw it away. It's
no
not-
blue. No, you're good.
This is a drink, actually. I finished my slushy out in the classroom.
Oh, okay.
This is just a cup with my drink.
All right. No blue lips today. Tomorrow. No blue lips.
I'll try.
Well, okay. So, arithmetic mean is adding the numbers up and dividing by what? How many there are, right? It's the average. Add them up, divide by how many there are. That's the mean that we know about. But that's not the only way to find the average of numbers. There's also a geometric mean. And so what I want you to do is, I want you just to ignore, let me see. I want you to, I didn't write it down on this one. I want you to just mark out after the X. I actually marked the X out, but after the X, mark that out. I don't think of geometric mean as a proportion, and here's why. Using a proportion to describe geometric mean only ever compares two quantities. But when you're finding the average of numbers, do you often have more than two numbers that you're finding the average of? So here's what I want you to think of the geometric mean as. I want you to think of it as, since there was two numbers, you multiplied them together. Notice with an arithmetic mean you would add them, but with a geometric mean you multiply them together. And then are we dividing here? We're square rooting. So isn't that actually like a 2 for a square root? You can actually find the geometric mean of lots of numbers. So if you had 3 numbers, you would go A times B times C, but you would do a cube root. And that would get you the geometric mean of 3 numbers. If you were going to get the geometric mean of 6 numbers, guess what your radical would be? A 6th root. And it's another way to find the average of numbers. What's kind of interesting is for EOC results, they had a suggestion on how to curve the grades or put them in the grade book, and it had a geometric mean in it. It was kind of strange. So the long story short, if you're finding the geometric mean, and you're only going to have to do 2 numbers, so that's why you have this formula right here. If you're going to find the geometric mean of 2 numbers, what do? You multiply them together and take a what? Square root, because there's 2 of them. Multiply them together and take a square root.
Really bad bloody nose. I need to go to the nurse's office.
You think so? Yeah, that thing's dripping like crazy. Yeah, pinch it real good and head on down. You're good. Your bloody nose is your pass. Yeah.
Your bloody nose leaked on the floor.
That's all right. That's all
No
right.
more of those in class.
Oh wait, we get to get out of.
I remember our first test of the year, Leighton. Do you remember that? Our first test? Yeah, I was like, great. Leighton's going to get bloody nose every test we have. That's what I thought, but no. All right.
I didn't know that. You drew it on your paper.
Yeah, that was a good time. Okay. Well, what do you guys get for the geometric mean?
44.1.
44.1.
Did you have to round it?
Yeah.
Yeah, okay.
Like 0.0.
So is everybody okay using their calculator?
Mr. Aiken,
Yeah.
for 2 numbers, did you just say like you really don't have to put that 2 in front of it because that's just what a normal.
A square root, it just automatically implies 2.
Oh,
Yep.
okay.
Okay, so ladies and gentlemen, that's our